Okay, so I think it's time to begin. Good morning, everyone. It's my great pleasure to be here and sharing this session, invited session on applied methods for causal inference. So today I have the honor to introduce Professor Matias Cataneo and Professor Jesse Chafiro, who will be presenting their work. Each of them will present for 30 minutes, and we will have 25 minutes of uninterrupted presentation. And feel free to write your questions in the chat, and we'll have 5 minutes at the end of each presentation to ask questions. I will try to collect the questions and ask them directly. So let's begin with Professor Matias Cataneo. He's a professor of operations research and financial engineer at Princeton University, where he's also an associate faculty at the Department of Economics, the Center for Statistics and Machine Learning, and the program in Latin American Studies. So Matias is a very well-published, well-known economist. So thank you for joining us, Matias, and please go ahead.
Great. Thank you so much, Sandra. Can you hear me well? Perfect. Great. So let me go. Actually, I'm going to turn this off because it's not working well. So it has too much statics. So let's fix that now. Okay, great. Let me just share the screen here. Okay, great. Can you see that well? I hope so. Perfect, perfect. Okay, great. Thank you so much for having me. It's a pleasure to be here and talking about this project called on bean scatter. It's joint work with Richard Crumb at the Federal Reserve Bank of New York, Max Farrell at University of Chicago, and Inje Feng, who just started at Tsinghua University. And this project has been an on and off in our research agenda. So we started back in 2018, and then we made some interesting push all the way to 2019. And then unfortunately, COVID came and put a big pause on everything in our lives, including these. And so finally, we got back to it about 6 months ago. And so if you have seen some version of this before, I promise I'll try to tell you a little bit about the new stuff that we have here as part of the project now. So I have a slide for about 50 minutes of a talk, but obviously it's only 25. So I'm going to skip half of them roughly. And the half I'm going to skip today is the theoretical portion of it, because I think this audience probably would benefit a lot more from understanding the core ideas and how to actually use it and what kind of things you can do and how this may address some of the issues that are currently ingrained in current practice and how they can actually be addressed or potentially fixed. So let me just start by saying that if you haven't heard about this before, bean scatter is a very popular microeconomics, applied microeconomics technique. You can find it quite a lot being used in economics, but also in other disciplines. So as I've been presenting more and more, I found out it's quite popular in marketing, and it has been used in epidemiology quite a bit, and other areas as well. And each of these areas use it in a slightly different way. Here I'm going to focus mostly on the version that was popularized, introduced and later popularized by a set of several authors, all part of the same research team one way or another. Here I happen to list four of them. I mean, Rush Cherry, I believe, is the first one who actually used it and introduced it in the literature, and then a sequence of other co-authors and students and collaborators picked up on that and continued using it, and eventually became, I believe, part of the standard toolkit in applied microeconomics. And I apologize to the many others that had been summarized by many others. And so I don't mean any disrespect to all the other great people who have been using these techniques. And nowadays you can find it pretty much in any applied micro paper that uses big data and tries to summarize relationships between an outcome of interest and some variables, independent variables under study. And so I'm going to go quick here in the interest of time, but let me just point out that if you read the paper, we do explain that this idea has been out there for a while. You can trace it back to notions like the regressogram in statistics, subclassification in causal inference, portfolio sorting in finance, regression tree in machine learning, and the list goes on. So in all these cases, the same strategy is being used, which essentially boils down to partitioning the data and then try to do some sort of local analysis within each of the partitions or bins, and that way try to model or understand better the local behavior or the local relationships between the outcome of interest and whatever variable you end up partitioning on. And so in this paper, what we're going to do is we're going to try to provide a foundational framework for understanding bean scatter, and it's going to basically build on 3 parts. When we came into this project, actually we came from the theoretical side. We had developed some theory, and we realized that it could be applied to this problem. Later, we realized actually we couldn't. We had to develop some new theory, but originally our goal was purely methodological. We just wanted to apply the theory that we had and try to understand the validity and potentially the invalidity of current practices. And in fact, along the way, we discovered that some of the most popular ways of doing things with this methodology turn out to be not quite correct in general, and they can actually lead to important misconceptions when you apply it to data. And so I'm going to talk about that a little bit more in this audience. I think people would benefit from perhaps this discussion, and then also see it in action, the different ways. So I will not talk about the theory, but the paper actually carries a little bit of new theory, which is more related to applied probability. It's a technique known as strong approximations, which is used to approximate the distribution of stochastic processes. But for today, I'm going to skip on all that. What is more important, however, is that we do provide software now also in Python. Originally, we had it in R and Stata. So this software is quite comprehensive. So it's going to pretty much offer everything that I'm going to talk about today and more. So in terms of linking this methodology to causal inference, I'm not going to talk about that today, but in the paper, we also discuss how to use the methodology to compare, for example, control and treatment groups and understand treatment effect heterogeneity, or, for example, optimal policy designs in terms of what would be the subgroup in the population that would potentially benefit the most from deploying a treatment and things like that. And so all that is discussed in the paper. So today I'm going to focus mostly on the very basics of the methodology, so I can at least convey some of the more basic ideas. If you're interested in checking the software, here is the website, and you can actually go there and download the different packages and look at them. So let me try to give you a quick overview of what bean scatter is, in case you haven't seen it before. So this is actually real data. It's one of the data sets we use in the paper. So the typical methodology of bean scatter starts by trying to understand the relationship of some independent variable X, potentially a treatment, on some variable of interest Y. And so this is just the scatter plot of the data. So basically it's a relationship which in principle looks somehow nonlinear between these variables. And what bean scatter typically do is first construct a sequence of beans. These beans essentially partition the support of the variable of interest. And then from that point on, the analysis is local in nature. So these beans are not evenly spaced. And the reason for that is because they are naturally usually constructed in terms of the quantiles of the distribution of the random variable X, the treatment variable or the independent variable of interest. And so from that perspective, that's a little bit of a different implementation in the sense that you need to estimate the quantiles first and then construct these breakpoints or knots. And those are random, so it will actually introduce some technical complexities in the analysis, but ultimately the methodology will provide can actually handle that. So these beans will have different lengths, but essentially they will have roughly the same number of observations in each of them because they are based on the quantiles of the X variable. So once you do that, then people typically look at some feature of the conditional distribution of Y given X in the bean. So a typical feature would be the conditional mean. And so these dots here, for example, correspond to the average outcome variable for the observations in the bean in question. So that would be an approximation of what is the average response of the variable Y, given that X belongs to that particular bean. And so once you do that, then typically people disregard the data, disregard the beans, and what they end up doing is just providing only the so many points or dots or that corresponds to whatever feature they're interested in. So in this example, I'm using the mean, but obviously you could also look at the median, you could look at the interquartile range, you can do several things within each mean, depending the particular interest in the analysis. So once they do that, they have these 10 or 20 or whatever number of means, and then they basically go ahead and typically contrast that with some parametric fit to the data. So in this example, for instance, I grab the data and I just run a linear regression, and then the linear regression on the raw data basically come out to be like this, right? And so this is a very common strategy in practice where they typically contrast the bin scatter, this sort of local approximation to a conditional expectation, with the global fit that a parametric linear regression, say, or polynomial regression would give you. And so to ground ideas, let me show you one paper. So this is a very prototypical picture that you will find in economics journals. So in this paper in particular, is written by Cherry, Friedman, and Rockoff. It came out in the AR in 2014. And this is a typical type of bin scatter picture that you will see. And so here I try to even match the colors. So these beans, these dots corresponds to the average for each of the beans. In this case, the authors decided to use 20 beans. In the previous example I gave you, I was using 10. So same idea. So you bin the support of the independent variable, and then you basically do the analysis within each of the beans. And then the red line here corresponds to this linear regression fit to the raw data. And so in this paper, for example, the authors used this picture to conclude from visual inspection that the relationship of teacher value added relative to the probability of attending college down the road for the students is actually linear. And so this has important implications for economics and for policy, because effectively saying that the marginal effect or even the elasticity of increasing teacher value added as a policy would actually have a constant effect in the population at all levels of teacher value added, right? So the increasing the 10% teacher value added at the lower end of the distribution will have the same effect that at the upper end of the distribution. And the author continue basically with the analysis by pretending that that relationship was constant and estimating an average effect across the population. So one of the things I want to try to talk about a little bit today is that actually this practice might not be the best practice in some settings. Actually, by doing this, you might have missed some non-linearities that would have occurred behind the scenes, and they are kind of hidden by the methodology. So I'll get that in a minute. And then even if you believe this is the right way to do things, then still perhaps doing a visual inspection of how close the dots are to the line might not be right in itself. I mean, typically we would like to formalize this idea by doing some sort of statistical test, where effectively we would ask questions like, how surprising it is that these dots are so far from the line in all these points, right? And so what you would do, basically, one thing that you could do is to ask the question, how surprising it is to see the largest deviation from the line, right? Or maybe the average deviation from the line, how surprising that average deviation is. And that is ultimately related to uncertainty quantification. In fact, each of these dots have some randomness attached to them, because obviously you are estimating the breakpoints of the beans, you're also estimating an average. So ideally, you would like to get some sort of notion of uncertainty quantification that would allow you to compare formally, statistically speaking, how surprising these departures from the line are. And if they're not very surprising, then you would be more confident, formally speaking, to actually accept the linearity assumption on the conditional expectation of y given x, for example. Okay, great. So that's basically the motivation of what the paper is about. So what we're going to try to do here is basically to tackle these problems from a formal perspective. And so what we do in the paper is first to provide a general framework for understanding bin scatter. And so in this context, what we do is a couple of things. So first and foremost, we try to respect practice as much as we can. So we're going to try to follow exactly what practitioners do in practice. So this includes, for example, binning using quantile estimates, which induces some additional complications. And then importantly also, we're going to try to discuss and understand how do you actually adjust for other covariates. So it turns out that this picture here I didn't tell you this until now, but it's actually not directly the relationship of going to college, in the indicator of going to college at age 20 against teacher value added, but also there is a bunch of other covariates that had been adjusted for in the analysis. And so depending how you adjust for covariates, things can actually go right or wrong very, very quickly. And so I'll talk about that in a little bit to try to understand how the adjustment should be done in order to be sure that you can uncover potential nonlinearities in the relationship of the variables of interest. Okay, then in the paper, we also do some extensions, which I'm not going to talk about a lot today, although I think they are important, at the very least, to try to put the methodology in perspective. So most practitioners still use the plain vanilla bean scatter, but there are a few things that you could do to actually make it better. And so we'll talk about that a little bit as I move forward, but ultimately it's just a generalization of the basic mean scatter ideas that are being used quite widely in practice. And then the final thing that we did in the paper, and this is kind of brand new, we finished it off a couple of months ago, we managed to extend all the results to a large class of nonlinear settings. So now we can actually handle quantile regression, logistic regression, Poisson regression, and all kind of nonlinear or semi-linear models. And so this actually expands the scope of the project quite a bit, because now you can ask questions not only about the average response, but also the quantile response, the interquantile range, and all these other quantities that practitioners tend to care about when they use this methodology. And so I'll talk about that a little bit towards the end. And then in terms of the main results, so there is a sequence of increasingly more difficult things that we do in this paper. So today, I'm not going to talk much about number 2, which is how to choose the beans. So that is given in the paper, but it's almost like a means to an end. It's just a way of formalizing and perhaps put more discipline on how you actually construct these beans. And then what I'll focus a lot more today is on how to do uncertainty quantification. So try to understand this idea that those dots are actually random, and as such, we would like to understand to what extent whenever we see a departure from the line, say, to what extent that is actually just sampling variability vis-a-vis a fundamental departure from the null hypothesis that postulates that the underlying relationship between y and x is actually linear. And so in order to do that, we need to understand uncertainty quantification, and that's part of what we do in the paper. And then we're going to use uncertainty quantification to do a bunch of interesting stuff for practitioners. So we're going to ask questions such as parametric specification of the relationships, but also we're going to ask questions about shape restrictions. Like, for example, is the relationship always increasing? Is the relationship convex, concave, and things like this? And so all this stuff we can actually do by means of our uncertainty quantification techniques. And so in that sense, you have all these already coded up in the software, and it will actually allow you to implement all these different hypothesis tests and be able to formally assess these questions beyond just using visual inspection. So the paper carries some theoretical novelty, but I'm going to skip it for today. And so let me reiterate that in the process of analyzing bean scatter, we actually found that some of the common practices are actually incorrect in general. And so I'll pause there for a little bit and try to give you a sense of what this means and how this it should be corrected. And in the process, we'll talk a little bit more about what are parameters of interest in this setting. Okay, cool. So let me just get started very quickly. So I'll do a 5-minute overview of the main ideas on how we actually build things. It's going to get slightly more technical in the process, but it's not that important. So hopefully you get to appreciate it. So in this context, the dots are again just the data, and the underlying relationship is artificial at this point. It's just this particular regression function of y given x. And we introduce artificially that bump because we would like to test for departures from the linearity of the relationship, or perhaps other interesting features in the underlying function. So what bean scatter does is basically, of course, only receives the data, and then with the data, you bin the data somehow, then you somehow fit these averages within beans, which could be understood as constant regressions with each bean, but effectively they are reported as a dot. And so how do you formalize that idea? Well, it's actually quite simple. What you do is you just postulate a very simple condition expectation regression type model. So you say the outcome of interest is related by some function mu that we don't know with a conditional mean zero restriction. And then the bean scatter is nothing more than just fitting a regression of the outcome of interest on a collection of dummy variables. So effectively indicator variables that tells you which observation to which bean belongs to. Each observation will only belong to one bean, and therefore by running this regression, what you're just doing is effectively computing the average of the outcome for each observation that belongs to a given bean, and then you get J averages. And so the outcome of this procedure is nothing more than giving you just the average in whatever bean the evaluation point X belongs to. So we formalize it this way because it would allow us to talk about extensions and what people do in practice. People typically don't do it this way. So when people go to the data, they just look at the data in each bean and compute the sample average. But if you put it in a regression setting, then it's very easy to expand it and to understand to what extent the methodology is valid and what problems you could carry along the way. And so this is a very basic setup of a bean scatter in practice. Let me remind you that the beans themselves are estimated. So we put hats on these things just to remind you that these are quantiles of the axis variables. And so they have been estimated themselves prior to the implementation of bean scatter. So then once you do that, you could easily just say, well, why don't you fit a linear regression instead of a constant regression within each bean? Right? So this is actually something that we saw in the literature done quite often. Sometimes people are interested in features that are related to the change of the function rather than the level of the function. So we've seen cases where people run linear regressions within each bean, and then they look at the slope of those regressions and ask questions such as, are they all positive? If they're all positive, then, well, that means that the function is increasing. If some of them are positive, some of them are negative, then that means that the function may not be increasing. Like here, for example, if you remember, the true function look like this. And so this slope here is telling you something about the change downwards of the function. Okay, great. So how do you, this is a quadratic example. So how do you actually formalize that idea? Well, now that we have our framework set up, it's actually quite easy. The same way that before we had the indicator variables for each bean, now we can just put in each of those beans the polynomial fit that we would like to implement. And so this is a Kronecker product, which just says implement this polynomial expansion for each of the beans. And then what you're just doing is constructing a slightly more complex basis, but at the end of the day, it's just a regression problem. You're still running the regression of Y on now these new covariates, and these covariates contain not just the indicator of which bean you belong to, but also along the way interacted with the polynomial order that you decided to use. And so this is pretty straightforward, so nothing very, very difficult. But then the other thing that is perhaps more interesting is once you are willing to implement more flexible fits within the beans, now you can also ask questions about, can we make them continuous? Can we make them differentiable? Can we do something like that? So for example, we can go from this to actually impose some constraints that would allow us to approximate the function, ensuring that the approximation is continuous, smooth, or things like this. And so that can actually be implemented. It turns out that is no more than a least squares constraint problem. So at this moment, what we're doing is actually introducing a matrix of constraints that, and I'm not giving you the formula here, but ultimately, intuitively, what it's doing is just saying, well, look, if you fit this regression here you are estimating intercept and slope, but when you move to the next bean, this point has to be connected. So the intercept has already been set for you in some sense. So these points need to be connected. And so you only have 1 degree of freedom left. You can only choose the slope, but you can no longer choose the intercept freely because these two lines have to connect at the boundary point. And so this idea can be, of course, generalized, and eventually you land into a system of constraints that effectively makes the problem constraint least squares. It's not very difficult to formalize, but actually it's useful from the perspective of understanding what's going on. And so then after that comes perhaps the more interesting punchline in the paper, which is this idea of how do we actually covariate adjust? So how do we actually enlarge this model to be able to account for other covariates and control for them? And so a very common practice that you would probably thought of if you came to this problem from the first time, you would say, well, if we are estimating the regression of Y given X, and we're just running a regression of Y on whatever basis you decided to use, then naturally you would like to put the covariates, perhaps in an additive separable way, and then try to estimate the quote-unquote long regression. So now the conditional expectation of y given x and w actually will just be this long regression, and it will just be adjusting for all these covariates w, as you see, is best. And that would be a perfectly sound thing to do.
Yes, you have 2 minutes.
Great. And so that would be a perfectly fine thing to do, but ultimately it's not what is done in practice. So in practice, what is done commonly is something that turns out to be not quite correct, which is that practitioners would first regress out the covariates and then construct the residuals, then regress out the outcomes and construct the residuals, and then actually construct the bin scatter just using those residuals instead. And it turns out that this practice actually leads to inconsistent estimates of the conditional expectation, not surprisingly, I guess, in general. So whenever the relationship is linear, that strategy would recover the relationship correctly, but whenever the conditional expectation is non-linear, this would actually fail. And so this red dots is an example of what would happen if you did it the way that the software that people commonly use do it. And what you would see is that obviously, even the support of the data is shrunk because, I mean, you're residualizing X, and therefore the support is shrunk, and also the linearity is kind of embedded in the construction. And so this is one of the main punchlines in the paper from a practical perspective. You have to be careful how you actually control for covariates in this type of methodology, because you can actually get results that are not quite what you wanted. So let me finish off one more line by saying that we also provide some uncertainty quantification based on bin scatter. So we are able to construct these confidence bands, and with them, we are able to construct a specification testing. And so this is the idea that I told you before. We can ask questions like, is it surprising for the dots to be away from the line? And so we can now actually run this test formally, and we can in fact answer questions such as, are these valid statistically significant departures that you should be worried about? Okay, let me just finish with 30 seconds, an overview of the project. So as I said, we give a formal statistical analysis of bin scatter, and we draw some attention on the importance of how you do actually covariate adjustment. Also, another thing I did not have time to talk about is we cover quantile regression, non-linear least squares regression, and other methodologies like that. And if you're interested in reading more, here are the references for you to take a look at. And well, as I said before, you can also download the software and try it yourself. Okay, so I'll stop here so you have time for questions either now or later. Thank you.
Thank you very much. There was an incredible efficiency of 50 slides. So are there any questions? I don't see any on the chat, but while they write them or someone has a question to ask, I wanted to ask in this last 3 minutes that we have, we could perhaps give us an executive summary of how do you optimally choose the number of beans. I know you said that you didn't have time to do it, but it would be great to have an idea of at least how to should.
Yeah, I can definitely go through that. So in the paper at the moment, so there are multiple ways of doing this. There is no one way to do it, I guess. It depends a little bit of what your goal is. So in this paper, what we chose to do is first and foremost try to construct something that is optimal in some sense. And so in this case, what we did is we actually focused on approximating the true function as best as possible given some metric. And so what we did is effectively we constructed an integrated mean square error metric. And so we compare the bin scatter fit relative to the function that you're trying to approximate or derivatives thereof, whatever you care about. And then we found an expansion that characterizes how much bias and how much variance this estimator in general has. And then we balance bias square and variance. And then based on that, we obtain a formula for the optimal number of bins. And actually we did that both for the traditional least squares based bin scatter, which is basically this one here, where you just run the regression on the bin scatter basis and the other covariates of interest as we recommend. But also we did it as well for the more generic nonlinear bin scatter. So this is something I didn't manage to take a lot about, but actually we covered a much more general case where we have some loss function, let's say quantile regression type, and then some link function, let's say logistic regression type. And then for that, we also developed the optimal number of bins, again, based on an integrated mean square error type expansion. And this model is actually richer because it allows you to think about what kind of parameters would you actually care about. So when you have these non-linearities, now you can start thinking about, do I care about the average effect, the marginal average effect, and things like this. So here are two examples of that. So this will be essentially the index evaluated at the link function, that will be the average effect. And then this one here will be something like the marginal effect. So you actually look at the first derivative of the postulated model for the condition expectation, and then you just look at the partial effect in that direction. Okay, great. So I'll stop here, but that's kind of the idea.
Super, thank you. There are a couple of other questions, but I think in the interest of time, we're going to stop here so that we give Professor Jesse Shapiro enough time to present as well. So thank you very much. It was a pleasure to learn from you. So now we're going to have a presentation by Professor Jesse Shapiro on bounds on a slope from size restrictions on economic shocks. So Professor Shapiro is a professor from Brown University. He's an Eastman Professor of Political Economy and an NDR Research Associate, also very well-known, published, and recognized in economics. So thank you very much for joining us, and please go ahead. You have 25 minutes.
Okay, thank you so much, Sandra. Can you just confirm one more time? Did you see the writing that I just did? Okay, yes. Great. And let me also just say, it was a real treat to see Matthias present that work. I've read this paper at some point, and Matthias and I have even emailed about it, but it's really, Matthias is an incredible teacher, so it was really cool to see the live version of the material with so much clarity. So thank you very much for coming and for the invitation. This is joint work with Marco and David. Both of them are here. And Marco is on the job market this year. So if you want, you can try to hire him in the chat. I would recommend it. And I would love to tell you about his job market paper, but that's not what I was hired to do today. So I'm going to tell you about this paper instead, which hopefully will also be of interest to some of you. So today we're going to look at a canonical problem in empirical economics, which is to learn the slope of some outcome. So that could be like the quantity demanded with respect to some input, say the price. Oh, I'll turn on my timer also so that I'm responsible. And we're going to be in the presence of some unobserved factor, say preferences, that might be related to the input. And we're going to imagine throughout that we have data from a time series of a finite time series of inputs and outputs. So for example, prices and quantities. Obviously, situations like this show up all over economics. Of course, in the canonical setting of agricultural economics that we often use in classrooms, but also in labor economics and macroeconomics and many other fields. Typically, if we want to say something about this parameter theta, this slope parameter, we need to impose some kind of structure on this unobserved factor epsilon. And obviously, different papers will take different approaches, but a very common one is to assume that epsilon is orthogonal to or independent of or mean independent of some observed variable, maybe an instrument or maybe the input itself. Today, we're going to look at learning about theta using a different route. And in particular, we're going to ask what we can learn about this parameter of interest, theta, if we're prepared to impose some bounds on how much the unobserved factor epsilon can change between adjacent periods. So to make it concrete, I'm going to illustrate with a specific application. And this application comes from a paper in the AR, which is about agricultural commodities, and in particular, and I'll maybe touch on this a little bit, learning about the effect of the US ethanol mandate. So this is a very highly cited and super interesting paper. And in this paper, we're studying the world market for staple food grains like corn and wheat. So Q here, that's the log quantity of grains consumed at the world level, measured in calories per capita. And P, that's the log of the average price of grains delivered in a given year, measured in dollars per calorie. And the data are going to be a time series of P and Q from 1960 through 2007. And the parameter I'm going to focus on today is the price elasticity of demand, which in this paper is an input to answering some important economic questions, including about the effects of that ethanol mandate. There are also other parameters that are of interest in this paper, and in our paper and appendices, we cover those as well. So here's the data from this paper. And so I've committed a little bit of a crime here by putting quantity on the y-axis instead of price, so apologies. I will not apologize for first differencing the data. That's actually really helpful in this setting. So I've done that with no apology. So what you're looking at is the change in quantity, in logs. So these are like percents, and against the change in price. And each dot is a year, or a pair of adjacent years, since these are inverse differences. And canonically, unless we know something about these demand shocks delta epsilon, we cannot conclude anything at all about the parameter of interest theta from a plot like this. We're left learning nothing about the parameter of interest. Now, in the paper, the authors address this problem using exclusion restrictions. And in particular, they treat shocks to agricultural yields as excluded instruments for prices. The reason that they don't take the more famous traditional route of using weather shocks directly is that these don't have sufficient power to yield informative inferences on the parameters of interest. So instead, they focus on shocks to yield themselves. And as you might imagine, because yields, which is just output per acre or hectare, might be a function of farmers' decisions, like what fertilizer they use and how intensively they farm and so on, this paper includes extensive discussion and sensitivity analysis related to potential violations of the exclusion restriction, and in particular related to the possibility that yields may be endogenous to prices. So you can see quotes like this throughout this paper, and I know like in my applied papers, I often have sentences like this, or even whole sections devoted to sentences like this, trying to defend my exclusion restrictions. And ultimately, I think this is a persuasive paper, and I think that the analysis in this paper is very reasonable. But what these quotes also suggest is that not everybody necessarily finds these assumptions transparently valid. And so today I want to explore a somewhat different route to learning about the price elasticity of demand in this setting that I think could have complemented the author's original approach. So to understand how we're going to approach learning about this demand elasticity theta in this setting, let's go back to the scatter plot, and let's think about this particular data point right here. Okay, in this 1 year, prices increased by, I don't know, let's call it 30%, okay, 30 log points or 30%. Quantities changed very little, let's call it 0, okay, I don't think that's quite right, but it's about that, okay. And so in this example, if we take delta Q to be about 0, and we take delta P to be about 3, if we suppose, for example, that demand is, say, unit elastic, so that theta is -1, then what we conclude is that there was a 30% increase in the demand for food within a single year. So all of a sudden, from 1 year to the next, people of the earth wanted to eat 30% more calories in food grains. And that seems like a really, really big change. The same kind of reasoning applies to many of the points on the scatter plot. So here's a plot that shows what all the implied shocks would be if we posited that world price demand for food is price elastic. Okay, or sorry, is unit elastic, unit price elastic. So if the elasticity of demand for food was -1, and what you can see is a lot of these shocks are really, really big. I find them implausibly big. So for example, here we're saying all of a sudden within a single year, people in the world wanted to eat more than 50% additional food calories from food grains. Okay, and that seems just too big. By contrast, if we posited that the price elasticity was, say, -0.1 instead of -1, we get a much more reasonable series of demand shocks, at least from my way of looking at things. So this way of looking at the problem suggests that we might be able to say something about what theta is reasonable if we can say something about what size delta epsilons are reasonable. And that's the approach that we take in our paper. So I'm going to take just a few minutes, just keeping an eye on the clock, to digress a bit from the application and talk now about the abstract setup. And then I'll come back to the application to apply it. So as we've seen in our application, but as holds more generally, for any slope that we posit, any theta that we posit, we can calculate the implied shock to the unobserved factor between any two adjacent periods. So in particular, here's that expression. We pick a theta, then we get an implied delta epsilon given that theta. Okay, that's very straightforward. Now I'm going to define this object m hat k of theta to be the k-mean of the absolute value of the implied of the sequence of implied shocks given theta. Okay, so this is just a generalized mean of the absolute value of the shocks implied by the given theta. If k is 1, this is an arithmetic mean. If k is 2, this is a root mean squared. If k equals infinity, then we're taking the maximum absolute shock implied by the particular theta. And I've put the maximum one in bold because for the purposes of the talk, that's what I'm going to focus on. It yields a nice geometric structure, but in the paper, you can see analysis covering a bigger range of k-means. Suppose that we're prepared to impose an upper bound on the shocks that we think are plausible. So in particular, we're going to conceptualize that by imagining we're willing to say that this k-mean cannot exceed some number b. So if k is infinity, this means we're saying we don't think that the maximum shock in any period in absolute value could plausibly be bigger than b. If we know that, then we know that the set of thetas that are consistent with that restriction, which is given by this set here, is an interval. Okay, so that's something that we show. So this characterizes the set of all thetas that satisfy this restriction, this first squiggly bracket thing. And then these square brackets, these give an interval that turns out to be the characterization of that set. And moreover, the limit points of that interval, theta lower bar and theta upper bar, are very easy to characterize and easy to compute so that we can work with them in practical settings very easily. So what's left here is to say something about what is a reasonable bound B. That's going to be the engine that drives this whole approach. So how can we say something about that? And to say something about that, it really only makes sense to try to do that in a particular application. You can't do that in all generality. So let's go back to our particular application of world demand for food grain. Economists have been studying the world demand for food for a really long time, and a lot is known about it. One of the things that this literature shows is that the major determinants of world demand for grain at the world level are world population and world income. We're doing everything in per capita terms, so we've kind of scaled population out of the problem, and that leaves income as an important remaining driver of shocks to world food demand. The income elasticity of world food demand is also a very widely studied economic parameter going back to Engel, at least, probably before. A recent survey article summarizes a variety of models of world food demand and finds that they imply income elasticities at the world level of between 0.09 and 0.37. So let's take a conservative approach and imagine that the income elasticity of world food demand is about 0.37. We can get annual data on log world GDP per capita, call that YT. And then we can ask, if this is the right income elasticity, what is the largest income-driven shock to world food demand over our sample period? So over these years, what is the largest shock to world food demand for food grain that's coming from income alone? And that turns out to be about 0.05. So let's just, for the sake of argument and illustration, imagine that we're prepared to give ourselves a little cushion and assume that there's no period over this sample from 1960 to 2007 in which the actual shock to world food demand is more than about 0.07. Okay, so that gives us like a little bit of a cushion to allow for the possibility that there might be shocks that are not driven by income, but driven by some other things. So that gives us a restriction that looks like this, that says that this m hat infinity, the maximum shock over this period, cannot exceed b. Now let's go back to our scatter plot and to our point of interest here that we highlighted before. Since we're working in first differences, we know that any demand curve has to pass through the origin, right? And because we're prepared to assume that the shock cannot have been more than 0.07, we also know that any demand curve has to pass through an interval of radius about 0.07 around this point. And moreover, if we're prepared to assume that the same bound applies uniformly over the sample, that is, we know that there's no period with a shock of more than 0.07, which again, I argued is kind of reasonable given what we know about this market, then we know that the demand curve has to pass through all of these intervals. So I've just drawn a radius of 0.07 around all of the points. And since we know, or we think we know, that as economists that demand slopes down, then we know that the demand curve must be one of the lines in this shaded region, because it has to be one of the lines that passes through all of the dotted intervals, right? It has to be downward sloping and pass through the origin. So this is a full characterization of the set of demand curves that are consistent with the structure that I've laid out. Now, all of this is assuming an upper bound of exactly 0.07, which I find kind of like a reasonable place to start. But of course, not everybody needs to agree with that. Some people might be prepared to impose an even tighter bound. Some people might want to impose a looser bound. Okay, so I didn't set this up in Zoom in the fancy way, but I'm going to run a little informal poll here in the chat. So here's a question for you, given what I've told you. Suppose that a researcher's estimate implies that holding food prices constant, the log of world food demand in calories per capita would have changed by more than B over 1 year between 1960 and 2007. For what value of B would you find the researcher's conclusion implausible? Okay, so one option is a value more than 5%, a value more than 6%, a value more than 7%. That's the one that I picked. A value more than 8%, value more than 9%, value more than 10%. Okay, so why don't you put in the chat your preferred B? Okay, Sandra's voting for 0.05. Do we have any other voters? Juan says 0.05. I think that makes it unanimous at 0.05. All right, okay, we got a 0.07. Thank you, that's my favorite too. Okay, that's good. All right, so we've got 2 here. This is few enough that I can actually tally them. All right, so, and people can feel free to keep putting that in if you guys want. But I will push on. So I guess part of the reason I paused that to ask this question is that our point of view is that different economists might find different bounds plausible. So it's not that we envision that a researcher should just defend a specific bound like 0.07 as the one most reasonable bound. Instead, a researcher that is interested in applying our approach might like to visualize the implications of a range of bounds so that different readers can reach different conclusions depending on the bounds that they find most plausible. And one way to implement that is with a plot like this, which we exhibit in our paper. So what are we showing you here? So on the x-axis, on the y-axis, we've got our parameter of interest, our theta. On the x-axis, we've got our bound B, okay? And notice that the x-axis is broken right here. And the reason is that there are some bounds that are sufficiently tight that actually they're rejected by the data in the model. So we can actually say that those bounds are not possible. And so another way of putting what we've learned here is that according to this analysis, there must have been at least one period in which the shock was at least 0.04. And that seems reasonable given what we calculated before based on income effects. Okay, so let me walk you through the rest of the plot. So here is the upper bound, and we've sort of truncated it at 0 to impose the sign constraint. And here is the lower bound. Okay, so according to this analysis, for any given bound B, the theta that explains the data must lie between this bound and this bound. So for example, if we go with my favorite 0.07, then we're going to learn that the elasticity of demand cannot be larger than 0.12 in absolute value. And that is an informative conclusion, I think. And one way to make that statement precise is that it is actually zooming in pretty close to the author's original confidence interval. So this is what the authors of the original paper conclude in their preferred specification. And it's pretty tightly contained in the interval that we get through our analysis. And indeed, one of the main qualitative conclusions that this paper reaches is that both demand and supply are quite price inelastic. So our approach would have given the authors another potential route to their conclusion. And here, we're not relying on any exclusion restrictions. Instead, we're relying on economic intuitions or arguments about the plausible size of the shocks to world food grain. And if the authors had put this kind of plot in their paper, they wouldn't have had to commit to any particular bound B because they would be letting different readers reach different conclusions based on whatever bound B they find reasonable. So they might have said, we think 0.07 is reasonable, but if you think 0.08 is reasonable, then you can learn from this plot too. Or if you, like Sandra and Juan, think 0.05 is reasonable, then you can also learn something from this plot. Everybody can walk away having learned something about the plausible magnitude of the slope parameter. So all of this assumes a homogeneous linear model, and that is something that we inherited from the original paper. So that is what this article assumes. So we've adopted that structure. And obviously many economic applications involve that kind of assumption. That said, we might be interested in allowing nonlinear functional relationships, and it turns out we can say something in that case as well. So in particular, we can generalize to a more general functional relationship that looks a little bit familiar from Matthias's presentation. And in this model, if we take first differences, what we get is that the change in quantity, change in Q between any adjacent periods, like the change in quantity, is given by the change in the unobserved factor, so like the preference shock, and the change in price multiplied now not by a universal slope parameter, but by an average slope. So this is the average slope of this function Q between periods t minus 1 and t. And in the paper, we also show that you can do essentially the same thing with suitable redefinitions with a non-separable model like this, which is also something that might be appealing in many economic applications. So if I have a bound, and you can see that very clearly from the structure of this equation, if I'm prepared to bound the absolute shock in a given period t, then I'm going to get a bound on the average slope between periods t minus 1 and t. And so because before we were looking at a bound on the largest slope, the bound on the largest shock also implies a bound on the shock in any given period, right? Because if I know the shock is never bigger than 0.07, then I know it's not bigger than 0.07 in any particular period t. And so that turns out to be a useful supposition, because if we impose that assumption, we get a bound on every average slope. And here it is. So here, what we're showing is on the x-axis is the year. So it's just like the points in our data set. And on the y-axis, we're depicting a range of slopes that are consistent with the bound of 0.07 on the absolute value of the shock in each year. When this range goes beyond unit elasticity, we have these little arrows. But what you can see is that actually a lot of the time it doesn't. So in more than 80% of the time periods, we can actually conclude that demand is inelastic, pricing elastic on average between period t minus 1 and t, just from this one assumption about the shock. So we can make, I think, very sharp conclusions about this function at each point, imposing no structure at all on how this Q wiggles or which way it moves or whatever, based on this one assumption. If we know something about the shape of the function, then of course we can say even more. So to illustrate that possibility, we've taken as proof of concept the case where we know that the function is polynomial of known degree. Okay, and then if we do that, we get this plot here. So what you're looking at here are the bounds we get on the average slope between period t minus 1 and t in each year from different assumptions about the maximum degree of the polynomial for this function Q. Okay, so if we assume the function has degree 1, then it's linear, and then we're back to the exact analysis I showed you before, and that's the 0.12 that you saw on the earlier plot. But what this plot shows is that you can allow for second degree polynomial, third degree polynomial, fourth degree polynomial, fifth degree, sixth degree. Sixth degree polynomial gets awfully wiggly on a domain like this. And even with a sixth degree polynomial, we can conclude that demand is inelastic everywhere. That is, in the sense that it's inelastic on average between all adjacent years in our data set. And in most years, we can actually conclude that demand is, for example, less elastic than 0.3. So we can get pretty informative conclusions about the price elasticity of demand from what I think of as sort of reasonable assumptions about the size of these shocks, and also pretty reasonable assumptions about like how wiggly this function, the world food demand function, might plausibly be. So my clock says 3 minutes. Does that line up with yours, Sandra? Okay, great. So then I'm going to try to quickly skip through one more thing. So everything I've done is in the setting of a single market, but we also might have a cross-section of markets. And in the paper, we have sort of details and notation about how to cast those kinds of a cross-section of markets into our setting. Here, I'm going to skip some notation, but instead, I'm just going to quickly illustrate with an example. So in this paper, the authors are interested in some of the macroeconomic consequences of interactions between men and women in the US labor market. And they're particularly interested in a parameter that governs the extent to which growth in female employment crowds out growth in male employment. And they estimate that parameter using a cross-section of US states. Okay, so here is their model. The outcome variable is the change in the male employment to population ratio from 1970 to 2016. The input variable is the change in the female employment to population ratio from 1970 to 2016. And this parameter, theta c, this measures the extent of crowding out of male employment by female employment. So if that's -1, roughly speaking, every woman who enters the labor market crowds one man out of the labor market. This is the author's data. Okay, so here I've got the change in female employment to population. I'm just watching the clock carefully. Here I've got the change in male employment to population. And what you can see is that the change in female employment to population was very large in all of these states and was very variable across US states. And of course, that's not surprising given what we know about the US labor market over this period. The change in male employment was usually negative, not that big, and not that variable. So it varies much less across states. As with our demand curve application, if we don't know anything about these shocks here, like the underlying shock to male employment or what would have happened to male employment absent the change in female employment, then we don't know anything about our parameter of interest, theta c. The authors address this problem by imposing exclusion restrictions. And they discuss, I won't talk much about what they are, but they discuss those restrictions extensively in a section of their paper called Threats to Identification, which suggests that some of the readers of the paper are concerned that the exclusion restrictions might not be valid. And I'm going to go through this very quickly because just in the interest of time. But in our paper, we argue that in this article, the authors could have reached conclusions very consonant with the ones that they reached using exclusion restrictions by adopting reasonable restrictions on the unobserved shock to male employment. Loosely speaking, we know that there were massive forces acting on female labor force participation during this period, and much less massive forces, but maybe important forces acting on male labor force participation. And if we embed that hypothesis in an assumption about the plausible size of the shock to male employment, we get a plot not so different from the one that I showed you before, and where we think we can learn something very informative about the parameter of interest. And in fact, pretty defensible bounds on the shock to male employment will imply an interval for the parameter of interest that's actually contained within the author's original confidence interval. So actually, in that sense, more informative than the author's original analysis. Okay, so my phone is beeping. So in conclusion, it's common to impose restrictions such as the orthogonality of shocks with respect to some observed variables for the purpose of learning a parameter of interest. But economists like you also have useful intuitions about the plausible magnitudes of unobserved shocks. And we show that these intuitions can be informative for parameters that we care about for answering economic questions. And I'll just make one philosophical pitch. If we have these intuitions, which I think we often do, and we don't use these intuitions, then we're leaving information on the table that could be helpful to us in answering questions that are important and that we care about. Thank you.
Thank you. That was fantastic. And thank you for keeping a careful eye on the time. So great presentations. Very thankful to you both for being here and joining us and spending the time to teach us about your research. Unfortunately, time's up, so I don't think we have a lot of time for questions. So I would invite all the attendants to email the authors to see if they can help you with your questions. But thank you everyone for being here, especially Professor Cataneo and Shapiro. It was a great pleasure to see you present.
Thank you very much. And I don't know what the deal is with the Zoom room, but I'm happy to stick around for a few minutes if there are questions.
Fantastic. So then that's great. If anyone
it's totally possible. We don't need this link right now, so you can stick around to ask questions if you want.
Okay, thank you very much, Juan. And by the way, Matthias, there were some questions for you in the chat.
Yes.
I forgot that I was going to tell you, but I forgot. I got too caught up in my own.
Thank you. Yeah. So I wanted to ask you a question. I'm going to use my chair position to ask you a question, which is so I imagine we need to use our knowledge and economic theory to choose the bounds. But can you this is always kind of problematic. So how do we justify these things, or do you have any suggestions as to where should we begin to do that?
Yeah, so I mean, in the setting that I showed you, basically what I'm arguing is you can just use what economists have learned about the market to say what's kind of reasonable. Like, we know, if you think about the world market for food grain, the biggest thing that's affecting world demand for that is income. And that's something that you can get from, I mean, this is, again, one of the most well-studied markets probably ever. And you know something about how much income is changing. And we know a lot about the income elasticity of food demand, not just from the time series, but also cross-section of countries, cross-section of people. And that's like a very well-studied, well-informed parameter, I think. Do we know it exactly? I don't know, but we have a reasonable idea of what it might be. So in that case, you can use that to get a number. I didn't get into this, but in the application to employment, what we say is, suppose that we're prepared to assume that the shock to male employment was, say, no bigger than half of the change in female employment in the state that has the largest change in female employment. That, I think, is a pretty mild restriction, given what we know about what happened to women's versus men's incentives to participate in the labor force and other factors during this period. So I regard that as like kind of reasonable. And we do the same thing. We say, what if it's a third? So that gives you a way to think about magnitude. I'm sort of opposed to fully automated approaches to things like this, but if you wanted one, you could take like the lowest feasible bound and like double it. And that would often, I think, give you something actually not so crazy. But I would advocate for using economics. And I guess the last thing I would say is just, we don't think it's a great idea to try to argue that, like, yes, the right bound is exactly 0.0692. I don't think that really is going to make sense. Just like I think when we're imposing exclusion restrictions, we don't really believe that orthogonality holds exactly, that like the expectation of the product of the unobserved variable and the observed variable is literally zero. We just think it's an approximation. And so what I would advocate in this kind of setting is to just depict what happens under a range of things that are kind of reasonable and let readers reach their conclusions. And I think in both of the papers that we study, this is something the authors could have done. And they would have, I think, been able to say that a reader who doesn't accept their exclusion restrictions should probably accept their conclusions anyway, or be prepared to defend why there are tremendous unobserved shocks offsetting the changes in prices or changes in female labor force participation in these settings.
Thank you. That was great. So yeah, there were a couple of questions for Professor Cataneo. One was from Oscar Mintic. It was about the bean size. So I think you briefly touched on this, but maybe it would be great if you could remind us as to should the beans be of equal size, or you think the best approach, the most recommended approach should be to use quantile-based beans?
Yeah, I just answered in the chat. So, I mean, the default and most people use is quantile spaced, but actually our software and the theory allows for evenly spaced beans. I mean, both are, just simple rules to position the nodes, right? So in fact, something that we're exploring now is whether we should perhaps bring some ideas from machine learning, in particular regression trees. So there is a sense in which you could form these partitions by minimizing some prediction error like regression trees do. This is a one-dimensional problem because ultimately the variable of interest is typically one dimension or two at most. Our theory has been done for one because it's what people like the most or use the most. And in these settings, this type of choices work typically, but you could think of other ways of positioning the beans. So yeah, that's what I have for that. Yeah. And then there is one more that says, oh, the optimal number. Well, again, the optimal number doesn't say much about the position, right? So you choose the position of the beans, people use this quantile spacing, and then the number of beans, so how many breaks you put in, is the question that we try to answer. And there we try to trade off bias and variance. It could be that, oh, I see, great. Sorry, I cannot talk and read at the same time. Okay, so what was I saying? Oh, yes, and then the actual number of beans can be chosen for other purposes. For example, if you care about testing or rejecting parametric specifications, you could actually choose the number of beans to maximize local power, for example. So we don't do that, but that could be done fairly straightforwardly, I think. It would be another way of doing it. And we don't have that done yet, but it would be a very natural thing to work on, I think. Cool, and I think that covers everything.
That's correct, yeah.
Great.
Well,
Okay.
thank you both. We won't take more of your time. I'm incredibly grateful for your time and for your generosity. So we'll probably see you soon.
Yeah.
Thank
Thank
you,
you.
Matthias.
Guys.
Thank you, Sandra.
Thank
Thank you,
you.
everybody.
Bye.
Bye,
Bye.
Jesse. Bye-bye.